Close your eyes for a second. Try to feel the sheer weight of your own consciousness. Right now, locked in the pitch-black vault of your skull, a 3-pound mass of wet biological circuitry is actively hallucinating the entire universe around you. Tech billionaires and pop philosophers want you to believe this is a trick. They want you to accept that your pain, your memories, and your existence are just cheap lines of code running on an alien server. Nick Bostrom published a paper about this. Elon Musk repeated it at cocktail parties. Millions of intelligent people nodded because, if we're honest, being a simulation feels more meaningful than being a random biological accident on a random rock orbiting a random star. Right now, the 3 pounds of tissue inside your skull is executing roughly 10 to the 17 synaptic operations every single second. Each one of those operations carries a thermodynamic price tag, a minimum heat cost that the universe refuses to waive for anyone. To simulate you, not the planet, not the solar system, just you, would consume more energy than our sun will produce across its entire 10 billion year lifetime. That is not poetry, that is arithmetic.
Let's start with the logic trap. The simulation hypothesis says we might live inside a computer simulation created by some advanced civilization. It's the Matrix, but without leather and probably worse lighting. The modern, rigorous version of this idea was framed as a trilemma. Either 1, almost all civilizations die before they can build ancestor simulations, or 2, advanced civilizations have no interest in simulating ancestors, or 3, we are almost certainly living in a simulation. If you reject 1 and 2, you're pushed to accept 3. Elegant, unsettling, and deliciously simple. But does simplicity equal truth? Not always. Before we judge, let's ask the right questions. What assumptions does the hypothesis rely on, and can those assumptions be tested? There are 3 big assumptions hiding behind the idea that we are simulated: computational feasibility, philosophical substrate-independence, and the statistical argument about observers. I'll take each in turn and throw in a few numbers, because people in lab coats like things with digits. First, computational feasibility. Can a civilization actually simulate a universe, or even just a paste of life like Earth, with people and weather and coffee stains, without inventing magic? A lot of the drama collapses once you do some back-of-the-envelope math. The human brain is often the benchmark. If you can simulate a brain, you can simulate minds. A conservative neuroscience estimate gives us roughly 10 to the 11th neurons and about 10 to the 14th synapses for a human brain. If we store 1 byte per synapse, tiny, tight, and optimistic, that's 100,000 gigabytes, about 91 terabytes. That's one person's memory map at a synapse resolution level. Multiply by millions or billions of simulated people, and you're well into exabytes and beyond. If each synapse needed more complex state, milliseconds of potentials, ion channel states, detailed biochemistry, the cost skyrockets. But raw storage isn't the whole story. To run a brain, you need operations per second, synaptic updates, spike propagation, short-term plasticity. If each synapse updates on average 100 times per second, reasonable for many networks, then a single brain needs about 10 to the 16th operations per second. That's 10 petaflops of sustained computation per person. A lot, but not unattainable in principle for an industrial civilization with huge computational infrastructure. The kicker is scale. Simulating billions of brains, plus entire planetary environments at fine detail, is an astronomical, pun intended, computing problem.
Now a reality check. There are physics-based limits on computation. Landauer's principle tells us there's a minimum thermodynamic energy cost to erase information. about 2.87 times 10 to the minus 21 joules per bit at room temperature. Sounds tiny, and it is tiny, but multiply that by the billions of bits you'd flip per second, and you get a real power bill. Still, thermodynamic limits are not showstoppers. They set bounds, not impossibilities. In short, computationally hard may be expensive, but not obviously physically impossible. So, an advanced civilization could plausibly have the hardware for simulations, if they want to build it. Second assumption, substrate-independence of consciousness. This is more philosophical than physical. It supposes that consciousness can be implemented on any sufficiently complex computational substrate, silicon, biological wetware, whatever. If true, emulating the functional structure of a brain should produce the same conscious experience. If false, then even a perfect simulation of our atoms may not produce conscious beings. This is a tricky philosophical knot. There's no experimental proof either way. It's a metaphysical leap we often smuggle into these debates. We assume minds are software, not irreducibly tied to carbon wetware. Third assumption, the statistical argument, often called the simulation argument proper. The idea is simple. If A, advanced civilizations can run many Ancestor-type simulations, and B, they do run a huge number of them, then the number of simulated conscious beings could vastly outnumber biological ones. By random sampling, you'd probably be in a simulation. That move converts computational plausibility into probabilistic inevitability. The great weakness is that it replaces one unknown with another. We don't know whether future civs will run Ancestor sims, and if they do, how many. Large numbers amplify uncertainty. They do not resolve it. So the empirical roots exist, but all are difficult and ambiguous. Now some math to show the sort of reasoning scientists actually use when testing these ideas. Remember our earlier synapse numbers, 10 to the 14th synapses, roughly 91 terabytes at 1 byte per synapse. If we require, say, 100 updates per second across those synapses, that's roughly 10 to the 16th updates per second, roughly 10 petaflops. Multiply that by 1 million simulated people, tiny compared to Earth's population, and you need 10 to the 22nd operations per second. Those are monstrous numbers. The upshot, if the future civilization is running such sims, either they have unfathomable compute or they limit the simulation in clever ways, coarse-grained physics, selective fidelity, or partial realism. That gives us a clue. If simulations are being run, they're probably not perfect atom-for-atom recreations of entire planets. They're optimized. Which brings us to a powerful critique, Occam's razor. The simulation hypothesis often flips Occam on its head. Instead of positing a simple, elegant underlying reality, it posits a more complex infrastructure behind everything. Why not accept the simpler explanation that reality is real, unless there's good reason to posit a simulator? Proponents counter that the simplest statistical expectation given multiple Ancestor simulation instances leads to the simulation being more likely, but that argument depends on debated priors. Bayesian inference is great, but garbage in yields garbage out. Another philosophical crack appears in the idea of Ancestor simulations themselves. If the goal of these simulations is to study history, they must be sufficiently accurate to produce the phenomena of interest. But many scientific phenomena are emergent and sensitive to tiny differences. If you fuzz out the microphysics to save compute, you might miss the very effects you'd want to study. So it's plausible that advanced simulators either simulate only what's needed, or they simulate at high fidelity but only for a tiny sample. Both options undermine the "we are almost certainly simulated" probability boost. Let's talk about falsifiability, because that's the heart of scientific respectability. A hypothesis that cannot be disconfirmed is not science, it's metaphysics. The simulation hypothesis can be made unfalsifiable by building simulators who intentionally erase evidence of their own existence inside the simulation. That's cheating. But if we restrict ourselves to the weaker claim that a simulation might leak detectable signatures, then it becomes at least partly testable. Look for Lorentz violations, search for anomalous cosmic ray cutoffs, examine statistical randomness in the cosmic microwave background, and scrutinize the quantum measurement problem. So far, no convincing leaks. Now for a thought experiment to sharpen intuitions. Imagine a future civilization that wants to study your neighborhood in detail. Not you personally, but social dynamics at the block level. It wants to run 1,000,000 Monte Carlo histories to understand how neighborhoods evolve. It will likely simplify, approximate molecules, simulate weather with fluid approximations, and model people as agents with compressed internal states. The simulation will be optimized for the questions the civilization cares about. That implies many simulations would be low fidelity in everyday details. You being conscious matters only if the simulation architecture preserves whatever substrate independence is required. That reduces the probability that your precise reality is a perfect, high-res copy. What about consciousness as evidence? Some argue that subjective experience feels real, and that such realism indicates a base reality. But that's a philosophical move. Your experience doesn't give a meta-ontological certificate. If you're simulated, you'd still have vivid experiences. That's the creep. The simulation hypothesis is consistent with virtually any observation you make inside the simulation, which makes falsification tough. So what is the best scientific stance? Skeptical, curious, and cautious. Simulation theory is a serious philosophical and occasionally scientific conversation starter. It has motivated, clever empirical proposals, which is good. The correct scientific attitude is to test the testable and admit the limits of the rest. If future experiments found Lorentz violations implying a lattice scale, or if cosmic ray spectra showed telltale anisotropies tied to a grid, that would be revolutionary. Until then, the hypothesis sits in a gray zone, interesting enough to discuss, but not yet evidence-backed. Now, every claim I have made in this video is mathematically specific and, in principle, falsifiable. If you can resolve the exponential scaling problem, I want to see your argument. I have opened the Community tab for exactly this purpose. Subscribe to the Cosmic Codex for more arguments built on evidence rather than assumption. And the next time someone tells you we are living in a simulation, ask them one question. How do you plan to classically simulate a Hilbert space of dimension 2 to the power of 10 to the power of 80? Then watch them change the subject. Until next time, demand the math.